let's continue. And if we like to solve the second set of the eigenpairs, and it means that we have already got the lambda 1 and the x1. And then the initial vector, we need to take out the component vector from the x1. Then we can get a vector like this one. It is the after the first iteration, we got the u1. Okay. Since we have already taken out the x1, then it is okay. The second iterations, we will multiply the A inverse B to the obtain the u1 again. So if we multiply the A inverse B to get the u1, you will find it will be equal to okay, it will be. So after several times, we can increase the okay after several iterations, we can get and we have already defined the lambda 2, the absolute value of the lambda 2 must be smaller than the absolute value of the lambda 3. So this ratio is less than 1. So the terms will close to zeros. So after several iterations, the um will close to the x2, and also we can calculate the Rayleigh quotient, and the Rayleigh quotient will approach to the eigenvalue of the x of the lambda 2. Okay, but remember we could have the numerical error when we calculate all no matter which result we got, it could have the numerical errors. Okay, so since we always have the numerical errors, so the obtained lambda 1 and the x1, we could have some errors. So when we calculate the u0 prime, and the alpha 1 is equal to is equal to the okay, so okay. But remember the x, no matter the x1 could have the errors. If we got the errors of the in the x1, then the calculated alpha 1 is not so accurate. So we could have the results, theoretically the results will be equal to the alpha 2 x2 plus alpha n x. Okay, but actually we could still have, if the alpha 1 is not so accurate, so we could have probably let's say 1% of the x1 still remained in the u0 prime vector. And even it is a very small portion of the x1 remained in the uz prime, then if you iterate, the results will approach to the x1, not the x2. Okay, so if we use the power method to solve the solutions, usually we need to do the same things for this so after we got the u1, for example, the u1 is equal to a inverse b u0 prime. We got the u1. We need to do the calculate the u1 prime, which is equal to the obtained u1 minus So we not only for the first time when we assume the b u0 and the u, we need to calculate the u0 prime. After the first iterations, we got the u1. We need to do the similar solution state. We need to take out the component vector of the x1 from the u1 again. So we need to use the u1 to calculate the u1 prime. And then at the next step, we will calculate, we need to use the u1 prime to calculate the u2. After we calculate the u2, we need to calculate the u2 prime. Okay, so in all the solution steps, we need to repeat the procedure to take out the x1 from the obtained um vectors. Okay, so in this way you can do the right, will approach to x2. So if we repeatedly to take out the x1 from the obtained vectors, then after several iterations, the vectors approach to parallel to the previous one. Or if you did the normalization to the obtained vectors, the vector will approach to the previous one. Then you can say, then you can stop the iterations, and the converged vector will approach to x2, and also the Rayleigh quotient will approach to lambda 2. Okay. So how can we get the lambda 3 and the x3? After and how can we get the lambda 3 and x3? And also assume an arbitrary u0. Okay, and the u0 will always be the x1 plus alpha 2 x2 plus alpha n x10. Okay, since we have already got the lambda 1 x1 and lambda 2 x2, then we can do the alpha 1 is equal to the x1 transpose b u0 divided by x1 transpose b x1, and alpha 2 will be the x2 transpose b u0 divided by x2 transpose b x2. Okay, so you can multiply the x2 transpose b to the vector. You will find only the second term will be non-zero. The first term, the third term, until the nth terms, since the eigenvectors, they are orthogonal to each other with respect to matrix A and also with respect to the matrix B. So if we multiply the x2 transpose b to the u0, only the second term, which is non-zero. And if we like to get the alpha 2, then we need to divide the results by the x2 transpose b x2. Then we can get the alpha 2. Then we can calculate the u0. You can say this u0 double prime is equal to original u0 minus So we will calculate the u0 double prime. And now the u0 must deduct the component vector from the x1, also deduct the component vector from the x2. Then theoretically, the vector will be the okay. So we can keep on multiplying the A inverse B to the obtained the U0 double prime to get the U1. And also you need to deduct the component vector from the x1 and the x2 again. Then you can get the U1 double prime. Okay. Then you can keep on going. Then you will converge to the x3, and the Rayleigh quotient will converge to the lambda 3. Okay. So that's the end of my introduction to the power method. And the power method includes the inverse iteration method and the direct iteration method. And the inverse iteration method will be the common one we will choose to solve the problems. Okay, since I will finish the eigenvalue problems today in today's lectures. So probably today's videos will be shorter than before. Okay, so I will take a break here.